Hi, welcome to everyone from around the world joining us today. I am Tim Holme, co-founder and CTO of QuantumScape, and I'm thrilled to welcome you all to another installment in the QuantumScape webinar series. I'm joined by Venkat Viswanathan of Carnegie Mellon to discuss the results of some of our independent testing of our tests, of our cells. But before we start, I'd like to share that we'll post this webinar to our website at quantumscape.com after the event concludes today. And also, please feel free to submit questions at any time in the Ask Question function on your console. And also, the report from the third-party test lab that we're discussing today is linked as a resource in the console for your reference if you're curious to dig deeper. So let me introduce Venkat Viswanathan. Venkat's an associate professor in the Department of Mechanical Engineering at Carnegie Mellon University. His research focuses on identifying scientific principles governing materials design, inorganic, organic, and biomaterials for novel energy conversion and storage routes. So we're grateful to have Venkat with us today to review and discuss these recent third-party test results. The last piece of the introduction here is that my presentation will contain some forward-looking statements, including data analysis, projections, and models based on our management's current expectations. So these forward-looking statements involve significant risks and uncertainties, and further information about our factors that could materially affect QuantumScape can be found in our SEC filings. So let's jump right into the main event that we're all here for. I think this right here is the punchline of this third-party test result, and let me orient you to what you're seeing. So this is a chart that shows the discharge energy of the batteries as they're cycling on the left y-axis, and the chamber temperature in the purple line on the right y-axis. So these cells were held at 25 degrees C as they cycled. The cycling conditions are listed down here on the chart. 1C charge, 1C discharge. So 1C, for those of you who don't know, means the battery is charging at a rate that would completely charge the battery in about 1 hour. So it's charging in an hour, discharging in an hour. Each cycle was done to full depth of discharge, that is between 0 and 100% of the state of charge at room temperature, like I said. And what this shows are 3 cells that are progressing together with very modest energy fade to 800 cycles. One thing that's interesting is 800 cycles. If you're thinking about a long-range electric car, that's about 300 miles of range. Then 800 cycles times 300 miles per cycle is 240,000 miles. That's a long-lived car. Not many people drive their car that long. So all 3 cells performed very similarly, and also very similarly to the data that we have previously released from cells that were tested in our own lab. The other details of the test condition are noted down here. The cathode thickness of 3.1 milliamp hours per square centimeter. What this means is the amount of charge that is accessed out of the cathode per area under these cycling conditions was that's characterized as 3.1 milliamp hours per square centimeter. At a 1C rate, that means the current density is 3 milliamps per square centimeter. And these are the cells that QuantumScape has, same genus of cells that QuantumScape has released before. It's an anode-free lithium metal anode cell of what we call a commercially relevant area, 70 millimeters by 85 millimeters, and under modest pressure of 3.4 atmospheres. These are single layer cells. So this is the main test result that the third-party lab tested and corroborated our independent tests.
Tim, if I could jump in here. Yeah, Tim, if I could jump in here. So I think this is really interesting, and one thing to orient sort of listeners here, right? This would functionally be like you would go take the QuantumScape cell in an EV to a supercharger all the time as it is today. So superchargers today take roughly about an hour to do the full depth of discharge, full depth of charge. So which means basically that this is sort of one of the hardest tests to pass, which is that it can deliver sort of full lifetime for about 240,000 miles, as Tim mentioned, at a supercharger all the time. And so I think this is pretty incredible and well beyond what most other lithium metal cells are capable of today, and on par or maybe even slightly better than where lithium-ion cells are today as well. So this is a pretty exciting result, and as Tim said, I think it's the punchline of the third-party testing report.
Yeah. And one other point to orient the listener here is that a typical battery would be rated as end of life when it reaches 80% of its initial capacity. So one of the targets that our commercial automotive partners have given us is cycling to 80% after 800 cycles. And what you can see is that all of these cells are at around 90%. So that is their cycle life is expected to be even greater than 800 cycles, even under these relatively extreme test conditions. Great. So let's dive a little bit deeper here. What we'll show you next is the actual voltage curves of selected cycles during this cycling test. So the blue curve that stands out a bit from the rest is the very initial charge that was done on the cells. So what you're seeing is as the time increases on the x-axis and voltage is increasing on the y-axis, this is a charge cycle. So the battery charges from its lower cutoff voltage up to its upper cutoff voltage. It's held there for some period of time. Then there's a little bit of a rest, and then there's a discharge as the voltage decreases. So this blue curve is the first cycle that was done at the test. And then the other cycles that you see in other colors laid on top of that are from roughly every 50 cycles throughout the rest of the cycling test. And so you can see that the performance cycle to cycle is really quite stable, that the voltage is increasing smoothly. It's just a very typical constant current, constant voltage test. There's no pulses or nothing else funny going on. And one other point that I'd like to note is why this blue curve is different from the rest. It's because the very first thing before the cycling test that the third-party test lab did was a very slow cycle at C/10, which means a 10-hour charge and discharge. When a 10-hour discharge is done to a battery, it reaches a very low state of charge, and so it can charge up a little bit more. So you'll see that this first charge is a little bit larger than the rest of the charges, but the first discharge is about the same. And so as the curves on the last slide reflected, the discharge capacity is very constant cycle to cycle throughout this test. Venkat, any thoughts to add here?
I think this was one of the highlights for me from the report when I first looked at it. I think kudos to the QuantumScape team for data transparency. This is something that I've asked for across the board and in the community, and I wrote this battery data genome perspective where we wanted people to be more transparent. Showing voltage traces like this gives you most of the information of what is happening. And I'd like to drill down a little bit in terms of the point you made about the fact that the shapes of the curve. The shapes of the curve tell you everything about what's going on. What's the kind of mechanism, what's the kind of fade, and so on. The fact that it's so similar across 800 cycles tells you that the cells are not only delivering the same kind of discharge energy, but functionally, mechanistically, there's nothing bad or parasitic going on. And if you had sort of other kinds of degradation modes that would be active, those would show up in this curve. Those would show up as weird shapes and change in the curvature of these lines. And the fact that that's not there means that the cell is not only stable in terms of delivering energy, but also behaves predictably. And being predictable is very, very important in terms of managing the battery cells in a pack. And so I think this is a really exciting result in my mind, probably one of the sort of the sort of gold in your report, so to speak.
Okay, well, yeah, thanks a lot for that perspective. So this is giving raw voltage versus time, but we can understand a little bit more from these curves if we do a bit of analysis. So on this next chart, what we're showing is the normalized discharge voltage across cycling. So what that means is you take the discharge voltage curve that we saw on the last slide, you take the average of the voltage, and then you compare how does that average voltage compare one cycle to the next. And so this is showing again for every 50 cycles throughout the test how that discharge voltage changes. And so what you can see is there's very modest change in the discharge voltage. There's about 1% change in the discharge voltage over these 800 cycles. So it's showing again, like Venkat was saying, stable performance of the battery one cycle to the next, predictable performance.
Yeah, this one I think is personally for me, quite interesting. One thing that is unique about the way QuantumScape reports their data is they show discharge energy, instead of just capacity. And the energy is a product of the voltage and the capacity. And famously, I think this was one of the great, great stories that we learned in the battery community, where there was a class of high nickel cathodes where the capacity was not fading at all, but the voltage was fading. And so eventually, from a customer's perspective, you need both capacity to not fade and the voltage to not fade. So if either one of them fail, then the overall energy delivered is much lower. That means lower range for your EV. And so it's very important that both don't fade. Of course, the first graph shows you that the product of those two are not fading. And this shows additional data that supports the fact that the voltage is not fading. Voltage fade, as popularized, I think, in Steve Levine's book, Powerhouse, was one of the main hurdles that prevented those kinds of cathodes to commercialize. And so the fact that we have such high quality discharge voltage retention as a function of cycle life, shows that the cell is quite stable.
Yeah, the chemistry that you were referring to, I think, is manganese rich. You might have misspoken.
Yeah, manganese. Yeah.
But these were the layered. Yeah, these are the layered compounds that had a lot of voltage fade. So we don't expect to see voltage fade out of our cathode active material because we're using a nickel-rich material. But if there is a lot of excessive impedance growth in the cell or resistance that crops up in the cell, then that will also manifest itself as decay in voltage. And so what you're seeing is that all of these in concert result in only 1% voltage fade throughout this test. Okay, so let's continue. There's a lot more metrics that we like to extract when we're doing cycling of batteries. So I think QuantumScape is not unique in this, but we do a lot of detailed mathematical analysis on each cycle of all the batteries that we test internally. So we're now showing this a little bit on some of the external tests as well. So this metric is one of voltage hysteresis. So it might not be familiar to those of you who don't live and breathe the world of batteries, so let me explain. On the last chart, what we were showing is the average discharge voltage during the course of a discharge per cycle. And you can do the same for the charge voltage. If you average the charge voltage throughout every cycle, you would get an average charge voltage. And the voltage hysteresis is just the difference between the average charge voltage and the average discharge voltage. Now, why is this important? Well, this voltage hysteresis represents losses in the battery. It represents inefficiency of the battery. So if the larger the hysteresis is, the more inefficiency the battery has as it cycles. And that means there's wasted energy on the grid and there's excess power that is dumped as heat into the battery. And so then the battery would need some active cooling potentially to avoid it from getting too hot if there are large inefficiencies. So what this chart is showing is that at a 1C rate, which is, like Venkat said, basically a supercharger charge rate, 1C rate of charge and discharge, the voltage hysteresis is still modest and relatively stable throughout cycling.
Yeah, maybe I'll add some color here. I think this is one of the things that I think there was a excellent paper by Jeff Dunn reporting a wide range of tests on their really high quality lithium-ion cells, and this is one of the metrics that Jeff asks to report in that paper. And the key point here is that the voltage hysteresis that we have here shows that the batteries are about 95% efficient. So it's losing about 0.2 over sort of a 4-volt 4-volt cell. So that means that the cell is extraordinarily efficient to begin with, and then it's of course staying efficient over the lifetime. This is comparable to some of the best lithium-ion cells. So this is, I think, pretty spectacular for a lithium metal cell, and well beyond the state of the art in terms of where other lithium metal cells are for this kind of charge discharge performance. For this kind of charge discharge performance, the QuantumScape cells, the data that we see here is much better than what any other lithium metal cell is capable of today.
All right, great. So let's continue. There are other things that you can extract from this cycling chart. One of them is coulombic efficiency. So when we were discussing voltage hysteresis and energy efficiency on the last slide, there's a different kind of efficiency that you can measure in a battery called coulombic efficiency. And this coulombic efficiency is how many charges do you put into the battery when you charge relative to how many charges do you take out of the battery when you discharge. So just think about if you were counting the electrons that go into a cell versus come out of a cell and take the ratio of those, that's the coulombic efficiency. And so this chart was shown in the third-party report, showing the coulombic efficiency every 50 cycles. But we actually want to concentrate on this next slide, which goes a little bit into even further detail that wasn't shown in the chart in the report. So this is the coulombic efficiency of all three cells on every cycle during the test. And if you just average all the data points here, the average coulombic efficiency is 99.995 roughly percent, which sounds like a pretty high number, pretty close to 100%. Maybe Venkat can explain why this is important and what the requirement for coulombic efficiency is.
Yeah, so coulombic efficiency is one of the sort of key metrics, and in the context of lithium metal, it's particularly important. Typically, in cells that involve liquid electrolytes in lithium metal, their coulombic efficiency is much lower than this number. And when you have a number that's maybe 99.9, that means that in a few tens of cycles, if you had no excess lithium, your cycle life would basically be, your capacity would degrade to about 80%. So in order to accommodate this, what is typically done in the liquid electrolyte world is they use an expensive lithium foil. So that's the way that they take around this problem. But because of this extraordinarily high coulombic efficiency that is basically on par with state-of-the-art lithium-ion batteries, what this means is that you can essentially now use an anode-free configuration and still get the cycle life that you want. And so I think coulombic efficiency is really the distinguishing factor that enables either anode-free cells or whether you have to use a lithium foil to reach the kind of cycle life you want. Of course, lithium foil is expensive, but lithium is also not very dense, so which means that you take a hit on the volumetric energy density, as well as a little bit on the gravimetric energy density. So coulombic efficiency is one of the key enabling factors to enabling an anode-free cell.
Yeah, that's right. Some people might be wondering why the coulombic efficiency is over 100% at times. There could be several reasons for this. One is that slight temperature excursions can make the battery capacity and voltage drift by just a little bit. I mean, please note that we are zoomed in quite a bit on this y-axis. So what looks like a large deviation is really a change from 100% to 100.1%. So we're very zoomed in here. But a further reason why you can have some noise here is we're actually down under the current resolution limits of these testers. So to get a much more precise measurement of coulombic efficiency, you would need a high precision Coulomb counter. And such devices are sold, but are not commonly used and were not used for this cycling test. So we're actually showing that the batteries are so efficient that they almost can't be measured by these standard measurement devices. Another way to sort of make this 99.995% roughly efficiency more tangible is think about 100,000 lithium atoms crossing the battery every charge and discharge, and 5 of them being lost somewhere. They wander off and react with some impurity in the battery or something like that. So that would roughly be 5 lithium atoms per 100,000 that get lost every cycle. So high coulombic efficiency is necessary. Another way to think about this is, suppose the coulombic efficiency of your battery were 99% and you didn't have any excess lithium foil, which Venkat said is expensive and occupies a lot of volume. So if you have no excess lithium foil and a 99% coulombic efficiency, you might think, wow, 99 sounds pretty good. That's almost 100, right? But a 99% coulombic efficiency would result in your battery being dead within about 23 cycles. If you use that definition that I described before as end of life at 80% of capacity. So even 99% coulombic efficiency is far from good enough. So the fact that these cells are showing very high coulombic efficiency is pleasing, but also necessary for the battery to have as long a cycle life as it demonstrated in that first chart that we showed first chart that we showed. Okay, so maybe now we can summarize for people. We talked about quite a bit just to make sure that it landed with folks. We can summarize. We showed the energy retention of the cells across 800 cycles in a real strenuous test. And that energy retention captures the two main types of performance degradation that are relevant to batteries, both the capacity loss and voltage fade. And so we showed that these 3 cells that were tested under room temperature and otherwise reasonable conditions and even accelerated conditions at 1 hour charge and discharge retained 80% of their capacity over 800 cycles, which would correspond to north of 240,000 miles of driving if the car has a 300-mile range. We talked about discharge energy rather than capacity because discharge energy is what matters to a driver. You need energy to drive a car, not just capacity, not just electrons. We talked a little bit about voltage fade, and you saw that voltage fade is caused by either a change in the cathode active material or resistance growth, and that all of those mechanisms combined showed only about a 1% decrease in the voltage over 800 cycles. And then we showed the hysteresis. We also showed coulombic efficiency of the batteries. So we talked about energy efficiency, which was roughly 95% under these conditions, and then coulombic efficiency, which was over 99.99%. So very few of the atoms are lost. There's one other point that I'd like to touch on, which is that we did this third-party testing primarily to demonstrate that our batteries and our test lab are well calibrated and align with what a third party would get. But this is not something that we intend to do on a regular routine basis. You know, we could spend a lot of time sort of going backwards in history and submitting every test that we do in-house or even that we release externally to a third-party test lab. But even if we did that, that wouldn't help us accelerate the time at which a customer could walk into a dealership and drive a car containing QuantumScape batteries. That's really our focus as a company, and so that's where most of our energy will remain dedicated. That is on our engineering efforts to move forward and accelerate our path to commercialization, and then sampling to customers, because at the end it's going to be an automotive company that puts our cells into a car and enables somebody to drive it. So that's where a lot of our focus will be going forward.
Maybe if I can jump in here, and I think this is something that I very much appreciate that QuantumScape did in terms of committing these resources to do third-party testing. And obviously, as you mentioned, Tim, there were a number of other metrics that were shown in the original report last December, and of all of them, I think the key one is that a battery expert would think would vary from test to test, location to location, different kinds of cyclers, different kinds of testers, and so on, is the cycle life test. That's where the highest variability comes. So I think it's great that your team chose to spend all that energy on that particular test. I think obviously some of the other tests around track cycle test that you showed, and I think 15-minute charge test and additional tests would have also been nice, but I think obviously the variability in those tests are very minimal. So I think the fact that the cycle life test is so close to the data that you had with QuantumScape testing, I think gives us good confidence that the internal data generation that's happening at QuantumScape is of high quality. Maybe I'd like to use this opportunity to chat a little bit about the fast charging question, right? I think, or I guess super fast charging or extreme fast charging, right? I think the goalposts are sort of shifting, right? So in the original showcase in December last year, you showed some really fast charging data, right? 15-minute charging. Now, the data that we've seen now is 1C, which is sort of like a supercharger all the time. And it's expected that, in the future, there are 350 kilowatt charger units that are coming. So they might be capable of 15-minute charging as you are envisioning. I think and of course, it's universally agreed that nobody is going to charge 15 minutes every single cycle, right? So, and I think there's sort of a lot of discussion in the community around sort of what the right ratio is in terms of that super fast charging cycle versus sort of normal charging, whether it's 1C or 1 hour charge or 5 hour charge. Can you provide some color on what that ratio is in terms of how many sort of super fast chargers you're expecting in terms of customer needs?
Yeah, well, I have to say your guess is as good as mine. I think a battery scientist doesn't necessarily know how all of the people drive their cars every day. But what I could speculate is that there's going to be a distribution. There'll be people who never fast charge, who charge at home all the time or charge at work and are just satisfied with that. There will be other people who drive a lot. Maybe they're on their road for the job. Maybe they drive an Uber. So maybe they're on the road and fast charging a whole lot. I think probably the core use case is people who fast charge only infrequently, the few times a year that they go on a road trip, and otherwise they'll charge at home or work or when they're out shopping or something like that at sort of either regular charge rates or supercharger rates, but not the 350 kilowatt style. I mean, 350 kilowatts is a lot of power. There are probably only a few places or a handful of places that are both near a main arterial highway and close enough to a grid that could supply multiple 350 kilowatt stations. So I think that kind of charging, my guess, like I said, there's going to be a distribution of use cases that'll be infrequent for most people. But I think a battery should be capable of handling, the relatively extreme tail of that distribution. So when we're testing a battery, we should demonstrate that, okay, if you're an Uber driver, this car will still work for your use case. So I think some of the extreme test conditions should be crafted with that use case in mind. I don't know, what are your thoughts?
Yeah, at a recent workshop, we discussed this topic, and someone jokingly said that you should call that the Venkat number and come up with a number for that ratio. Of course, as a battery scientist, I'm also speculating, but I think, I love speculating, and I've done a few of these kinds of thought pieces. I think about 3 to 5 is a good ratio in terms of sort of overall use on average for customers. So about, somewhere between 3 to 5 extreme fast charge amid sort of, set of normal chargers. And I think that, of course, as you said, Tim, I think it's important to sort of come up with standards of how to test them and so on. I think we're entering a new era where, we are seeing these kinds of chargers being available and the performance becoming battery limited, right? Before it was the charger power limit, but now that the chargers are there, it's on the battery scientists to deliver that kind of performance such that we can utilize that level of power. So I think there's some talk around that number being 10, so 1 in 10, which seems rather low to me because on average, if you think about sort of your use cases, right? I think the key point here is that even if you drive a lot many more days in residential zones, the amount of driving you do is much lower than when you go out on a trip, in which case you will do many more such fast charging cycles. So I think the ratio is more like 3 to 5 in my mind, not 10. So I think that's a evolving landscape, and I think one that I think will be very important for fast charging in the future.
Yeah. Okay, great. So C/5 charging maybe is not the all the time use case. All right, so I see questions pouring in. Before we get to those, I do want to give a little bit of bonus to folks, and then we'll turn to Q&A. So this is data that we just released on Tuesday showing 10-layer cells meeting the milestone that we had laid out. This was our, last year we set up a series of 4 major milestones for the company to accomplish in 2021. And the last one of those was to show a 10-layer cell cycling under basically all the same conditions that we had a 1-layer cell cycling in. So over 800 cycles to over 80%. And on Tuesday, we announced that we had done that. This is the data from that cell showing that it's close to 90% after 800 cycles, as our 1-layer cells were. This was tested at a rate slightly north of 1C, actually 1.2C charge and discharge rates with average current density around 3 milliamps per centimeter squared. So the way the math works out here, this cathode loading was that I described earlier of how much capacity do you have per area of the cathode was 2.5 milliamp hours per square centimeter. So when you run that at 3 milliamps, you get 1.2 C rates. So this cathode loading is a bit lower than what we had shown on previous cells. And I think one of the main reasons for that is that we measured this cathode loading at this, what turned out to be a 1.2 C rate. So at a slightly higher rate. It just happened that for these cells, we were doing faster capacity check cycling than we had done previously. So that's one reason to see slightly lower cathode loading. But it's not something at all systematic. Like we wouldn't expect that as we further increase layer count, the cathode loading would decrease. Actually, we intend to increase cathode loading above 3 milliamp hours per square centimeter going forward. Maybe one other point to note here is this was tested at a pressure of 3.4 atmospheres, as have most of the other cells that we've presented on. This is a relatively modest pressure. You know, for reference, lithium-ion cells are at something like 0.5 to 1 atmosphere, and this helps because as lithium moves in the battery, layers expand and contract, which is called a swelling or breathing in the battery. And a modest pressure helps keep all the components next to each other and keep the resistance low. So this pressure that was applied to our 10-layer cell is just the same as a 1-layer cell, indicating you don't need to increase pressure as you increase the layer count. Really, pressure is going through all the layers in the normal direction. So pressure you apply to the first layer is applied to all the layers below that. I think there's been some misconceptions about that. So these are some of the points to note about this result. Venkat, anything further that you wanted to note?
No, I think this I think I think this shows that the stacking has not caused any further issue, and I think the pressure point that you brought up is very important. That one of the sort of concerns when the single layer cell data was presented was that when you stack them up, would you need more pressure? Would it uniformly transmit across all the layers, and questions of that kind. So I think the fact that the performance is similar to what you had in the single layer cell shows that there's basically the architecture is robust and is capable of scaling.
Yeah, well, kudos to the rest of our team here. This was the culmination of a lot of work here. We needed to make more cells, get more material through our line and on test. So it required a lot of process engineering and just contributions throughout the organization. As people who followed some of Elon's statements about manufacturing being hard would attest, when you scale up, you can't take things for granted. There's just a lot of blocking and tackling that has to be done. All right, let's dive into some of the Q&A now. So we've got questions, and I guess we'll just keep taking them until the earlier of our time runs out and we run out of questions. So the first one that I see here is, with this cell, the single layer cell as a building block, what energy density we expect to achieve as we get prototype and commercial samples for automotive OEMs. So we didn't say the energy density of this cell basically because energy density is a ratio of two factors, energy divided by mass or volume of the cell. In a single layer cell, or even a 10-layer cell for that matter, the numerator is modest and the denominator is kind of large because you have cell packaging. So if you imagine the following scenario, you're trying to eat an orange. How much of the orange do you get to eat versus how much is the peel that you have to throw away? The orange peel is the denominator, or the overhead in this case. So the structure that optimizes surface area per volume would be a sphere that has the most volume per surface area. So you want to make your batteries as, in one sense, as spherical as possible. A sphere doesn't make very good sense for our battery design and for packing them together into a pack, but we need to make them into what look like more like bricks that will stack together and have a lot of internal volume. So as we increase the layer count into the dozens of layers, we'll increase the energy density of our cells. And if you go to our website, we do have some projections on there of energy density that we could achieve throughout time as our cells mature. And there was a question also for Venkat here. Venkat, can you put energy density in the context of where lithium ion is today and where it's expected to be in the next few years?
Yeah, so I think lithium-ion batteries have been growing at a rate. The energy density has been growing at a rate of about between 3 to 5% on average. Closer approaching 5 now over the last few years. So which means that if you project that out, we're expecting cells to be in the energy density to be in the specific energy of about 300, approaching 300, and going a little over 300 in the near term. And so until this step change to either lithium metal or silicon is sort of unlocked, I think we'll sort of gradually go in this sort of slow 4% trend. So I think this is why it's so critical to bring next generation battery chemistries to market.
Yeah, great. And energy density is one of the calling cards of a lithium metal cell, especially a lithium-free anode lithium metal cell, because you get to do away with the entire anode of graphite material, which is a significant fraction of the volume of the cell. So energy density should be a benefit and is one of our calling cards. All right, next question is, the lower cutoff volts showed 3 volts. Please confirm that this reflects 100% depth of discharge. So the questioner is referring to this slide where we were showing our raw voltage traces. So yes, batteries are typically cycled between a lower and upper cutoff voltage, and that's exactly what's shown here. So lower voltage was 3 volts, upper voltage was 4.2 volts. That was the cycling range. And when we say 100% depth of discharge, that's what we mean. It's cycling between those voltages. Then the next question follows that one. Is there a CV, constant voltage step for each charge? Yeah, that's what's shown here. So there's a constant current step during the charge until it hits the maximum voltage of 4.2 volts. Then there's a constant voltage step right here until some end condition, which is either based on time or current falling below a threshold before the battery then switches into this rest and then discharge. So to battery insiders, this is called CCCV charging, constant current, constant voltage, and that was what was happening with these cells.
Tim, maybe I think there's an interesting science question here, which is that one of the reasons why, there's of course a couple of different factors why the constant voltage region exists, right? One is of course to ensure that there's no lithium plating on the graphite side, and of course about electrolyte degradation. So there's a couple of different factors there. With the fact that, and this is the point I made in the showcase event last December, right, is that you turned a bug into a feature, which is that graphite fails by lithium plating, and your mechanism of operation is lithium plating. Do you imagine that the protocols for charging a lithium metal cell in the future is likely to be substantially different than CCCV because of the fact that you've now relaxed the constraint of avoiding lithium plating?
Yeah, that's a good question, an interesting area. I know that we're not alone in thinking about these issues. If you look at academic journal reports, there are a lot of reports about how do you optimize charging protocols for, you could optimize for various things, life of the battery or how fast the fast charge actually happens, various factors. So yeah, I think this is an area where some are doing research, and it's interesting. This test is showing CCCV, but that's far from the only way to charge a battery. That's just probably the most conventional way. Got it.
And I think maybe I'll throw some to you so that maybe the Q&A formats are more vibrant. I think apparently there's been multiple questions on whether 15-minute charging, whether that will be supported, and I guess why that was not there in the most recent data release.
Yeah, so we do still target 15-minute charge rates, and in our battery showcase last December, we showed cells that were charging at that 4C rate. We didn't include that because, like I was saying in the summary slide, what we wanted to do was pick the test that reflected sort of very close to real-world use conditions or even accelerated real-world use conditions over many cycles, 800 cycles, and replicate that test just to show that our cells and our testing methodology is sound. And we don't intend to do a lot further external testing here. We think that the most important external testing is with our customers. And so that's where the focus is for external testing. It's we'll send samples to customers and have them test them in their labs.
Good. Okay, maybe we can do a few rapid fire. There are some very easy ones about the QS cell in cold weather compared to lithium ion.
Yeah, good. So again, if you refer back to the battery showcase that is on YouTube and on our website, we showed the battery cycling at -10°C. We also showed discharges of battery materials down to -30°C. So what we're hearing from car companies is that the lower end of the temperature is around -20 to -30°C. And so we intend the battery to be operational throughout that range.
Okay, great. And I think this one's easy. Impedance value, why has that not been given?
Yeah, so we didn't show impedance. It's not something you can extract immediately off of CCCV cycling, although you could analyze the rest at that top of charge. But we did show normalized discharge voltage on this slide, and also the hysteresis. And that, I think, gives you a pretty good estimate of what is the internal impedance of the cell.
Yeah, I think I'll add a quick commentary here. I think the impedance is an intermediate quantity. The discharge energy and the discharge voltage and the capacity fade are the more relevant quantities. So I think to focus on the key metrics here, I think the discharge voltage over life is probably the more relevant metric to show, and which was shown. Okay, I think there's maybe a little bit more discussion that we can have on the pressure question, which is around how much, what is the stack pressure of 3.4 atmosphere, and how that gets manifested in terms of a battery pack, and whether there might be some, the packaging question that you gave a very nice analogy with the orange. So the question now is, is it going to be, more like an orange, or is it going to be like a pomegranate, right, in terms of packaging? So can we talk a little bit about the sort of pressure and how pressure gets implemented in packs?
Yeah. So at the highest level, it's something like a clamp that applies pressure to a cell. It might be implemented with bands or straps, something like that. But what you should look for is this pressure modest enough that it can be designed around at the pack level or at the module level? And what we're hearing from our customers with car companies is that they're saying, don't go to extreme lengths to bring pressure down below 3 atmospheres. 3 atmospheres is something you can handle. And if it causes great pain in the battery chemistry level to reduce pressures below 3, that's maybe not a trade-off worth making. However, once you get to pressures above 10 atmospheres or so, then it starts to become really a lot less workable from the car perspective. There's more volume, mass, and cost in this clamp mechanism or whatever is going to apply pressures. One other thing to add is that we have shown some zero pressure data where we showed cells cycling past 1,200 cycles actually with no extra pressure applied to them. And that's an area that we're going to continue to work on. Okay, now let me ask you a question then. So this was a question directed at you. So it says, you touched on this with respect to coulombic efficiency, but could you touch on what accounts for the relative strength of the QuantumScape batteries and chemistry compared to other known competitors' pathways? It says competitors don't seem to release such test results, and then how confident can we feel about any comparisons that we make between QuantumScape and competitors?
Yeah, so I think the real challenge, as I think we all have talked about here, is the unforgiving AND test that a battery has to satisfy, right? The Boolean logic, which is that everything has to be yes for the cell to be usable in a car. And so I think the first one in that is probably coulombic efficiency, because that directly translates to cycle life. And of course, the unfortunate thing is that it's not directly released most of the time, so it has to be inferred indirectly. And so the way in which one can infer coulombic efficiency of lithium metal cells especially is to look at how much lithium foil they had. And there's actually a very nice analysis that we put out in a paper in the Proceedings of the National Academy of Sciences last year that shows the trade-off and the thickness. Once you know the thickness of the lithium foil that is being used and the cycle life that they are getting, then you can use that to back calculate what the coulombic efficiency that those cells have. And I think, it's now, quite clear that the liquid cells are about 99, but well below the 99.99 numbers that was shown here. And so as a result, they have to make the compromise. All lithium metal cells that use liquid electrolytes have to make the compromise of using a lithium foil.
Okay, so that lithium foil with liquid electrolytes, you think is maybe something fundamental that they might require?
I think it's been getting better. I think the question was, how, of course, there's been extraordinary progress over the last 3-4 years in liquid electrolytes and the performance of liquid electrolytes. They are still far from, of course, it gets exponentially hard as you try to approach that 99.999 plus number with liquid electrolytes. Of course, there's been massive progress in terms of, coulombic efficiencies that were in the 95s to now, things that are in the 99s. I think there is still sort of an uphill battle for the liquid electrolyte cells as well. And of course, it's an active area of research, and I think there's a lot of progress happening there. But I think the question of whether it can reach those levels, lithium is one of the most reactive elements in the world, right? So which means that if you put that in contact with a liquid, I think it's a very, very challenging task to stabilize that completely. So I think it's a challenging challenge for the liquid electrolyte folks to address that.
Okay. Yeah, and I know you do a lot of research on that in your lab, so we're talking to an expert on that particular subject. All right, well, here's a quick one. Is QuantumScape ever going to release a sample with beyond 12 to 14 layers? This seems only reasonable for the scale of vehicles to be realistic. So yes, we will. What we're saying is that our next year will be making batteries with up to dozens of layers. So we think that the specific layer count is going to depend on the automotive OEM that we're working with. They'll all have their own particular specifications related to what current and voltage they want to get out of the cell and how they want to stack those into a module, what physically fits into a module, what electrical properties they want to have related to series count and parallel count and so forth. But yes, we do fully intend to make cells beyond 12 or 14 layers. That's clearly required. Okay, another question was, what is the production timeline for our batteries? So what we're planning is that we'll be spending 2022 setting up our pilot line, and then batteries hopefully will be rolling off of that pilot line in 2023 that we can deliver to automotive partners that they can use to drive test fleets, test cars around, start collecting a lot of data. And then based on that, we're going to be building, or we plan to be building larger factories after that and commercializing in the 24-25 timeline in high volume. Here's a question that maybe Venkat could take. Can you comment on the safety aspects of a lithium metal battery or a solid state battery versus lithium ion?
Yeah, so I think the safety is I think the main challenge that has been hindering lithium metal cells from commercializing. In fact, one of the first lithium ion batteries technically commercialized from Moly was based on lithium metal, but they were promptly recalled because of the safety issues related to dendrites. Which now I think is quite clear with the kind of data that has been shown that dendrite resistance is clearly demonstrated for these solid state lithium metal cells. I think the safety aspect is certainly depends on a few factors. One is the cell certainly still has some liquid electrolyte on the cathode side, of course, albeit now you've removed the electrolyte on the anode side. So certainly the safety profile for a cell that has overall lower liquid electrolyte content is better. And of course, now you have a solid electrolyte that stops lithium plating and dendrite formation as a failure mechanism. So I think that also provides another layer of safety in terms of suppressing one of the failure modes that is present most commonly in lithium metal cells, but also in lithium ion cells, where lithium plating and then eventually growing through the separator and then shorting the cell is one of the failure modes. So additionally, I think there's a lot of sort of other aspects that solid state enables in terms of now you have a a ceramic. So the ceramic has a higher heat capacity and the ability to sort of manage the temperature that might come from the release. So I think there are some aspects there that also plays
on that point. On that point in particular, the ceramic, it's stable to quite high temperatures, many hundreds of degrees Celsius. So compared to a lithium-ion battery where the separator is a polymer, the polymer will go through two different phases if in a safety event. At first, it'll start to melt and some of the pores will close down, which prevents further contacts between anode and cathode. And that's beneficial. It's called a separator shutdown mechanism. But then as the temperature increases beyond that, the separator will actually melt and peel back and then expose more contact area between anode and cathode. And so this is when you can get into thermal runaway events. And by replacing this polymer that can melt with a ceramic that's basically like a rock, right? It'll get hot, but it's not going to melt until it gets extraordinarily hot. So I think it'll act as a brake on these thermal runaway events. However, what we've been talking about so far are essentially theoretical concerns. We will have to, be doing safety testing on larger cells that have a high energy content. And so to the point of the question of when does safety testing become relevant, it's really when we are making large commercial intent area cells that have the high energy content, where the orange is a significant fraction of the orange plus peel that you can then get a meaningful safety test. So I think we're getting near the end of time. I'd like to have a few closing statements. Maybe I could give Venkat a chance to provide any final remarks or takeaways from today.
Yeah, I think one thing I'd like to start by saying, and this was actually one of the opening remarks that was made in the event that Tim, you and Andrew Ng did with Steve Levine, is that I really feel, and we wrote this in this perspective, that battery data and releasing high quality battery data that shows all of the metrics is, I think, a really key cornerstone for battery development in the coming years. I think batteries are moving from being this sort of nascent industry to something that is crucial in many countries' goals to achieving net zero. Right? I think we were just, we witnessed a couple of weeks of very exciting developments at the COP26, and I think batteries and next generation batteries are at the heart of that transition, and it's really, really important that battery companies take battery data quite seriously and releasing the sort of right metrics so that we can all assess how good these cells are and how good they will be in that sort of 2025 timeframe when the sort of the battle for supremacy, in a sense, is going to be fought. So I think in that sense, I'm very excited, and in fact, to me, this is the whole sort of third-party testing, third-party validation, and the data release is all music to my ears. And I'm so glad that that QuantumScape went ahead and did this. So I think that's sort of on the sort of data part. I think this is something that I would encourage all of the other commercial efforts as well as academic efforts to be transparent about your battery data, right? And I think it's important to recognize that that of course there's a lot of proprietary knowledge in making batteries, but the data, in a sense, is not proprietary. I think it's very hard to reverse engineer anything from just the data. So I think it's very, very important that all of the data is put in. And so I think that's quite crucial. And I think the second aspect is the sort of comprehensive nature of the data set. I think it's very, very important that when you release your data set on performance, you do that under what should be uncompromised testing conditions, right? So you should ensure that they're being tested at commercially relevant conditions and factors and so on. And if not, right, I think it's very important to acknowledge where the gaps are and then address those gaps. I think in that sense, this particular event, and I think that both the data sets as well as the progress you've made with your multi-layer cells is great. Of course, as you, I guess, alluded to, there's still ways to go, and I think lots of challenging, scale-up things are up ahead, and I'm very much looking forward to sort of, what lies ahead in the coming years for your team's development. Thanks for the opportunity to join this.
Yeah, well, thanks a lot. Yeah, so looking ahead and dovetailing off of that comment, we will have lots of scale up and manufacturing challenges ahead of us. So if these are the kinds of challenges that excite you, our team is growing very rapidly. Please come to quantumscape.com and look for the link to our careers page. We have, I don't know, last time I counted out something like 100 job openings posted on our website, and we're growing very rapidly. We're looking for high quality people who want to help us solve battery challenges. So please do come and apply if this is the kind of thing that interests you. And then the second comment about looking ahead is what we were talking about today was really NMC, a nickel-based chemistry that is the most popular in EVs today. But one of the other things that will be coming online increasingly is lithium iron phosphate, LFP. Tesla and Volkswagen and other car companies have mentioned that going with low nickel is going to be a really key part of the future, because not only because of the cost of nickel, but also just the availability. So iron is much cheaper and much higher availability in the supply chain. Our battery platform is really based around a separator and anode technology, and it's more or less agnostic to cathodes. So we have released a little bit of data showing that our chemistry is, at least at a first pass, quite compatible with LFP. So this is an area where we'll continue to have a few forays into, and then eventually let our customers decide what proportion of cells do they want to be selling with nickel versus iron in them. And it would be our intention to support either one based on where the customers are going. So thanks a lot, everyone, to joining us today and spending your morning talking about batteries with us. It's been fun. We really relish the opportunity to show a deeper look into how our cells perform, because we think, honestly, that the performance is quite good. It's something to be proud of and worthy of investigating a bit. So thanks all for joining us, and have a good rest of your day.